Hi, welcome back. We're going to pick up from section or part C from section 2.3, our basic differentiation formulas. So part C is on our very first application that we're going to look at this semester. We really have three big applications that we use derivatives for in calculus and in engineering, and that is this first initial one about velocity and acceleration and position. The derivatives help you with that. Then later on this semester, we look at related rates, and we also look at optimization problems, which are all basic derivative applications in the real world. So we're going to start with this part C, which is looking at the difference between position, velocity, acceleration, and how all of that helps you figure out your speed, whether you're speeding up, slowing down, which direction you're going. There's a lot of things that all of this tells you. And this is one of those applications that's, for some of you, a little bit hard to understand because of the positive and negative signs. So I hope that when we're through with this, and then what we do in class as well, that you will have a better feel for how all of this works, okay? All right, so we're going to start by just kind of looking at these basic definitions. So it says, if the motion position function of a particle is known, then we can find the velocity and acceleration functions in the following way. If the position of a particle is given by f of x, then the velocity of the particle is given by f prime of x. All right, now I talked about this in an earlier section on the notes, and we did this kind of trying to get our heads wrapped around what kind of notation we're going to see. So if they give you a position function f of x, then the derivative f prime would be the velocity of that function. Okay, so that's number one. If you have the velocity of a function, okay, then the acceleration would be the derivative of that. So I don't like the fact that we use g because that looks like a totally new function. So I kind of want this to go in line here. So if our original position is f of x and the velocity is f prime, then let's say if the velocity is given, and we're going to call that f prime, right? That's the same thing here. Then we can find the acceleration by doing the derivative of the velocity, which would be the second derivative, okay? Because typically you wouldn't do an acceleration problem without figuring out the velocity. So typically you're going to get given the function, you find f prime, the velocity, you find f double prime, the acceleration, okay? So, and that's kind of what it says down here. So we can also say that if a position is given f of x, and then the acceleration would be the second derivative, okay? So it's typically more how it looks. Now, I also told you that in most calculus problems, you're not going to see f of x. You're going to see these notations. So instead of f of x, they're going to give you the position, which is your original function, s of t. So I'm going to put over here, this is going to be like f of x. Okay, this is the original function. So on these problems, when you're given a function, that's your position function. Okay? That's how you figure out where the particle or whatever it is you're looking at, where it is. Okay? So if you need a position, you would do the original function. The velocity is going to be denoted as v of t, which makes sense. V for velocity. So that's kind of easy, but remember that is the same thing as f prime, right? So the velocity would be the derivative, in this case, of the position. Then you have the acceleration function, which is the derivative of the velocity. So in your head, we're thinking of that as the second derivative, okay? So there's all of these notations get a little confusing, so that's why I'm spending a little bit of time on this, but it just takes a little getting used to. So it says, then v of t is the same thing as the derivative of the position, which it is, right? Because if you're so it's just another way to say s prime. So you might write s prime of t, but that's the same thing as v of t. So that's what that's saying there. And then the same thing here. If the acceleration is the derivative of v, That would be v prime, but it would also be the second derivative of the original. So you can write it anyway, but you need to understand when you're reading a problem what's given to you. So you kind of need to know all of those things. So in my book, I'm just always knowing that we start with the position, first derivative is velocity, second derivative is acceleration, and I always do that no matter what. No matter what the notation is, that's what I know. Okay? All right, so let's look at this first example. Okay? It says a particle's position is described by the function s of t equals 3t cubed minus 144t. T is measured in seconds, and s of t, the position, where it is measured in feet. Okay? Find the velocity function, find the acceleration function. So that's just two basic things to make sure that we understand. Okay? So the velocity function, v of t, is the same thing as the derivative of the original position function. You don't have to write both of these. I just want to make sure you understand. That's the same thing this is asking. So we would do our rule for our power rule. So 3 times 3, that's 9 t squared, subtract 1. And then there's your linear term, so minus 144. So that would be your velocity function. All right, part B is asking for the acceleration function. So this is all you need to write. All right, that stands for acceleration. But again, that is the derivative of this. So we could say v prime of t. Okay. Or you could even go as far as saying the second derivative of the original position function. So all of these are the same. This is all you need. But again, just to kind of explain what we're doing. So that would be the derivative of this. So 2 times 9 is 18t. So here's your velocity function. Here is your acceleration function. Okay? All right. So what I want to look at just real quick is how this all works in terms of this function. So here's our position. So again, I'm just sketching, okay? I know the y-intercept of this function is 0, and I know the direction. So let's say it looks something like this. Goes through 0. Okay? So here is s of t, the position, where this thing is at any given point in time. And since we're doing t is measured in seconds, then this part of the graph isn't really important to us because there's no such thing as time, negative time, right? So we're really just looking at this part of the function, but still, it's the whole thing when we're graphing and looking at things. All right, so let's look at 9t squared minus 144, okay? That's a definite parabola, right? This is the y-intercept. So I know that this parabola kind of looks like that, and I'm going to just highlight that real quick. Okay, so here's the derivative function. Now, kind of go back to what we've been doing in class. Okay, so this is v of t. So think about it. Here is negative 144, okay? That is where the slope is the steepest, and that always is right here. This tangent line is steepest right here on the curve. Here is where the tangent line is 0, right? Your max and mins. So that represents those 2 points right here. Okay. And then again, all of the derivatives on this side of your original function are positive. So everything from the left side of this graph is positive, so that's why it's above the x-axis. All of the slopes between here and here are negative, right? All of your tangent line slopes are negative. So notice all of the tangents or their slopes are down here, which are negative numbers. This being the steepest, so that's why that's the lowest. And then again, everything to the right of this tangent line of 0, all of these slopes are positive, so all of those points are above the x-axis because these are positive numbers. And the higher we get, the steeper the slope. Okay, so just kind of looking at what we were working on in class, the picture does kind of help because it makes sense to kind of what we're doing. All right, now, what's the acceleration function? Well, the acceleration function is 18t. That's just a line with a very steep slope. Slope is 18, the y-intercept is 0. So the acceleration function is a function like this, right? Here's a of t. Well, remember, that's the derivatives of all of these points, right? It's the derivative of the derivative. So where is the only place on the derivative, on the velocity, where your tangent line is 0? That's down here at the bottom. And that's the only place where the derivative is 0. And then everything to the right of 0 is positive up here. Everything to the left of 0, these slopes are all negative. So that's why that line's down here. Okay, so they do match up. And it takes a little while to see, but that's what we're working towards, is getting all of you guys to see that by the end of the semester. Okay, so let's finish off the problem. Find the acceleration after 9 seconds. Well, you know, looking at this graph, if I go to 9 on this graph, it's way up here, right? Way up here. So it's going to be a big number. But how do you find it? You would just plug in 9 into the acceleration. So we would find a of 9, and we would do 18 times 9. Okay, and 18 times 9, 162. Now, acceleration, because it's the second derivative, has square units. So we would say that's 162 feet per second squared. Okay? Again, your velocity would just be feet per second, and then your acceleration, a second derivative, the units would be squared. Okay, now part D says find the acceleration when the velocity is 0. So this is kind of a two-part problem. You guys got to understand what you're being asked. Find the acceleration, okay? So we're going to be using this formula, but what are we plugging in this formula? For t, we need to figure out the time, right? When is the time when the velocity is 0? So the first thing I need to do, find when the velocity is 0. Okay, then find a of this number right here. Okay, a of that. So the first thing I have to do is figure out the time when the velocity is 0, then find a at that time. That would give me the acceleration. Okay, well, look at your velocity function. Where is the velocity going to be equal to 0? That would be here and here, right? Now again, I don't need this is going to be a negative number for time, so we're going to rule that out. So basically we're looking for this value right here. Okay? So we're going to take the velocity function, set it equal to 0. So we're going to do v of t. We're going to see where that equals 0. So here's your velocity function. So when does 9t squared minus 144 equal 0? So that's easy to solve. Move the 144 over to the other side, make it positive. Divide 144 by 9, you get 16. So we end up with t equaling plus or minus 4. But remember, no such thing as negative 4 seconds, right? That doesn't exist in real life. So we're only looking at things from 0 on for time. So that means our time would be 4. Okay? So at 4 seconds, the velocity equals 0. All right, so now we know when the velocity is 0, at 4. So now we want to find the acceleration at 4, which would be on this graph, right? The acceleration, again, if I plug 4, it's going to be way up here. So, but that's what we're going to do. So now we can find a of 4. Okay. So what is a of 4? We're going to go into the derivative, the acceleration function, 18t. And instead of t, we're going to use 4. And 18 times 4 is 72. And again, that's acceleration. So that's feet per second squared. Okay, 72 feet per second squared. So again, the big part about these kind of problems is you understand what it is you're being asked. Some of you would say, oh, I would just do a of 0. No. Okay. So this is the important part. Do you understand what you're asking and what function are you putting in what values? So that's why I always like to draw pictures. You don't have to know the pictures, but it helps to kind of see what's going on. Okay. All right, so we're going to try another one, number 23. Same type of problem, a couple different types of questions. Okay. All right. So number 23 says we have a particle's position, and now we have the function s of t equals t cubed minus 9t squared plus 15t plus 10. T is measured in seconds, and s of t is measured in feet again. Okay, so I want to look at this function just so I can kind of see what's going on. So, you can put these in your calculator. I'm just sketching. All I need to know is what is the y-intercept, so I know it crosses at 10, and then the shape of this graph. So I know it's going to cross at 10, and it's going to come from this direction. Right, it's going to come up and come back like this. Again, I don't know exactly how high up and down it goes, but this is just giving me an idea. And again, I don't really need stuff over here. My graph is starting when t is 0, right? When the time is 0, and then the time is going to get positive. So if I'm looking for roots or things, this number is not important to me because there is no such thing as a negative time, right? So I'm really in the first and the fourth quadrant, okay? All right, so just so I kind of have an idea of what's going on. So now we're going to find the velocity function. And I already know that it's going to be a parabola, t squared, right? So I kind of already know that, but I can graph it now based on this. So let's find the velocity function. It's the derivative of the position. So take the derivative of this would be 3t squared. Derivative of the next term would be negative 18t. And then the derivative of that linear term is just 15. So there's your velocity. Okay? All right, well, now I see what this is. Okay? So I know where the derivative is equal to 0 at the max and min, so right about here, right about here. I know this is the y-intercept up at 15. Okay? So I'm just going to kind of sketch my parabola. Okay, here's the velocity. Here's the position. Right? And I don't know that from looking at this, but I do know from my original function, whatever this time is, that's here and this. So I'm getting ready to find those numbers now. But just so you can kind of see what's going on. Didn't ask you to graph this, this is going on in my head. So I have an idea of where slopes are positive, where slopes are negative, where things should be on this graph, okay? All right, so what is the velocity after 3 seconds? What is the velocity after 3 seconds? So I'm just going to plug in 3 into the velocity. So 3 times 3 squared minus 18 times 3 plus 15. Okay? So we've got 3 times 9, 27, minus 18 times 3, that's 54, plus 15. It's going to give you negative 12 feet per second. Now, let's take a look at our graph. Negative 12 feet per second, the velocity at 3. Okay? So, if I am looking at this graph right, the velocity of every point from 0 to the max would be positive, right? Positive slopes. Any velocity, which is the slope of the derivative, from here to the min would be negative. So that means 3 seconds has to fall in here somewhere because it's got a negative velocity. And let me please remind you of this now, and we'll keep talking about it. But because velocity is negative does not mean you are slowing down. That is a speed, okay? It's a speed and a direction. So all I know here is that I am moving 12 feet per second, but I'm going backwards, okay? The easiest way I can tell you this is, and I think I mentioned this before, is if you think about riding your bike or driving your car to and from school, let's say from where you live. So if you get in your car, okay, and you drive to school and you're driving, this is a position, maybe how far away you are from your house, okay? This is maybe how far you get from your house in one direction. Let's say you were going north, but then you forgot something, okay? If you forgot something and you start going back home, you don't go back on the graph. You would turn around and go in the opposite direction, okay? So negative velocities mean you are going in the opposite direction, but that is you're moving forward, okay? You're not going to drive backwards. You're going to turn your car around and still drive. So that's what that means. It just means that you're on a part of this graph that is heading downward because it has a negative slope. Okay? All right. Well, when is the particle at rest? Okay. So what does that mean? When is the time? So this means at what time, and the particle is at rest, meaning the velocity would be 0, right? Velocity is movement. So at what time is velocity equal to 0? That's what you're being asked right there. Okay, so that means I'm going to take the velocity, 3t squared plus minus 18t plus 15, set it equal to 0. We want to find the time, when. So we're looking for the t's. So again, we're going to factor that, and we can start by factoring out a 3 from each term. Factor what's left. So we're going to use 5 and 1. Both will be minus. So set those equal to 0. We end up with t equals 1 and t equals 5. And these are seconds. Okay. So on my graph, I now know that at 1 second and 5 seconds, that's when the velocity was equal to 0. So now I know this is 1 second on my graph, and this right here is 5 seconds. It's the only two places on the graph. So I knew I was going to get two answers. Here they were. Okay. So my position at 1 second is way up here. Okay. My position at 5 seconds is way down here. But the speed at 1 and 5 seconds, I was not moving. Tangent is 0. I was not moving. Maybe there was a light. Maybe I was making that U-turn to go back home. Okay. So right here, I stopped. And usually you got to stop to turn around. And that's not always true on a bike or car, but on a picture, there's going to be a little split second where your velocity is 0. Okay. All right. Let's look at part D. When is the particle moving in a positive direction? Okay. When is the particle moving in a positive direction? Well, I can kind of see it from here, but we're going to do it on the number line just because a lot of you don't do this over here. But I know that I'm moving in a positive direction from here to here. And then I'm moving in a positive direction from here to here. Okay? That's where my tangent lines are positive. So I can kind of see that. So I kind of already know the answer. But let's look at how we would do that if you didn't have the graph. Okay? So I found where my velocity was 0. And I want my position to be positive. So like right here, I know at 3 seconds I was moving in a negative. So I was not moving in a positive direction. I was moving backwards. So what you're going to do, and I always label my number lines because otherwise you're going to get them confused because sometimes we need more than one. Actually, there's not going to be an arrow there. Let's put a bracket because this is 0. So we don't need to go past 0, right? There's 0. All right. So I didn't draw an arrow because remember, we don't care about negative time. It's not going to hurt you to put a 0, but it will on your answer because you don't want your interval to say negative infinity to something. You're always going to start at 0 with real life problems with time. Okay. So you're going to mark the times where your velocity was 0. So here's 1 and here's 5. And then what you do is you just pick some numbers in these intervals. You guys know how to do test points. You've done them before. So I'm going to pick a test point in each of these three intervals to see whether the velocity is positive or negative. So this is if I didn't have that graph right there. Okay. So I know at 3, I already have 3. I've already done 3 because I put it in right here. So I know between 1 and 5 seconds, the velocities are going to be negative. Okay. I already did my test point. My test point was the number 3. Okay. So now I need a test point here. So maybe I would use 1/2. And then I need something over here to test, maybe 6 or 7 or 10 or whatever you want. Now, where are you testing these numbers? Right here, okay? It didn't ask me about the position. It said, when is the particle moving in a positive direction? Okay, that's your velocity. So I'm going to plug in 1/2. And the easiest way to plug in 1/2, I mean, you can put this in your calculator and just use your table, or I just worry about the sign. I don't really care what the value is. I just care, is it going to be a positive or negative number? So if I put 1/2 in, and I always do the factors. So if I put 1/2 in here, 1/2 minus 1 is a negative number. And if I put 1/2 in here, 1/2 minus 5 is a negative number. So that means I'm doing a positive number times a negative number times a negative number. And a positive times a negative is positive. So I know that any number over here is going to give me a positive value. Then I'm going to do the same thing with a number over here, 7. If I put 7 in here, this factor is positive. If I put 7 in here, this factor will be positive. And now I've got a positive 3 times this positive number times this positive number, positive. Okay? So when is the particle moving in a positive direction? I would say from 0 to 1 seconds. So I'm going to write it out, 0 to 1 second. And 5 and on, right? And 5 seconds and beyond. That's the words. Okay. Mathematically, 0 to 1 second, 0 to 1, and 5 to infinity. Okay. Now, remember when you do intervals, we're not including these. Why can't we include those? Because those are where it equals 0. Okay, it's where it was equal to 0. 0 is not a positive or negative number. Okay, so we need to go parentheses. That's what's going on. Okay, so from 0 to 1 and 5 to infinity, which again, go back to the graph, that makes sense. Here's time is 0, here's where the time is 1, right? And then here's where the time is 5, and up. And those are where your positive derivatives are, where the slope would be a positive number. All right, part E. When is the particle slowing down? Another thing that some of you guys have some issues with. So, slowing down is not just acceleration, okay? So, just kind of going through your velocity, when I have a velocity function and I plug in numbers, that tells me a direction that that force is going. So the velocity is the direction and the speed you're going. Well, acceleration gives you the force behind that speed, right? So if you're doing acceleration, just because an acceleration is positive doesn't alone mean you're speeding up. Your velocity must also be positive, okay? So the forces have to be the same sign for you to be speeding up. So let me say that again. So if the velocity is positive, like over here, and you find your acceleration to be positive over here, then yes, you are speeding up. But if the velocity is positive over here, but your acceleration is negative, then you are slowing down. So on the reverse side, if your velocity is negative and your acceleration is negative, you're speeding up, okay? Because they're both heading in that direction. Negative is the direction. But if your velocity is negative and your acceleration is positive, then you'd be slowing down. And on a graph, it is kind of easy to see when you speed up and when you slow down. You always are speeding up, moving towards a max or min, but as you get close to the max or min, you're going to slow down so you can turn around. So I always kind of think about it on a graph. This is where I'm slowing down. Then I'm going to speed up over here, okay? And then as I get to this point, I'm going to slow down again. So my plus and minuses kind of make sense with the graph on what kind of, if I'm speeding up or slowing down. All right, so for slowing down or speeding up, I need to look at the velocity and the acceleration, okay? So first off, let's find the acceleration function, which is the derivative of the velocity, which remember, where's our velocity? So we're going to find the derivative of this. So we would do 3 times 2 is 6t minus 18. Right? So a of t would be the derivative of v of t. So that is 6t minus 18. All right, so to figure out where that's positive and negative, I need to find out where it's 0 so I can do my little number line. I need an acceleration number line, okay? So we're going to take the acceleration, we're going to set it equal to 0. So we get 6t equals 18, so t is 3. So this is where the acceleration equals 0, okay? So my a of t graph, start at 0, we only have 3. Okay, this is acceleration. Let's see what's going on both sides of 3. So if I use a test point over here, let's say I'm going to use 1. That's easy enough to plug it in here. So if I put 1 in here, 6 times 1 is 6. 6 minus 18 is a negative number. And then use something bigger than 3, let's say 5. Plug 5 in here, 30 minus 18 is a positive number. All right, now that alone is not going to tell me, this is not just slowing down right here, okay? This is when the acceleration is negative, but I need to compare it to this. So here's the way we're going to compare. So we're going to say compare b of t and a of t, okay? So we need all the numbers that were included. So we need to plot 1, 5, and we also need to now plot 3. So we're going to take our number line. So here's 1, 3, 5, okay? And then we need to put plus and minuses for the velocity and for the acceleration, okay? Well, hang on, I should have left room for that. Thank goodness for whiteout. Okay, let me put that back up a little bit. All right, so let's put b of t here, a of t here. So I need to put plus or minus signs there. All right, so let's look at our velocity. So between 0 and 1 second, the velocity was positive. Between 1 and 3, what was the velocity? Okay, the velocity between 1 and 5 was negative. So obviously between 1 and 3, it's negative. And between 3 and 5, it's negative. And then after 5, the velocity became positive. Okay, now we're going to do the same thing with our acceleration. I know my acceleration was negative between 0 and 3. So acceleration between 0 and 1 would be negative, and between 1 and 3, because that's that part right here. And then anything after 3 was positive. So the acceleration from 3 to 5 was positive, and from 5 on. Now I can answer this question. A particle is slowing down where the acceleration and the velocity are different. 1 plus, 1 minus. So here's where we were slowing down, and right here. Okay, so write that in terms of interval. So we are slowing down between 0 and 1 seconds and 3 to 5 seconds. Okay, that's when we were slowing down. Now, take that back to the graph, and did that make sense to what I said earlier? 0 to 1, 3 to 5. Well, look what was happening from 0 to 1. I was getting ready to turn around, so yes, that should be slowing down. And then from 3 to 5, getting closer to turning around again. So this is part of the graph where I should be slowing down. So that did work, okay? Again, you don't need that graph up there, but the number lines are what we're going to be using. I always just like to do the graphs because it's nice to know that what I'm seeing is making sense with the numbers that I'm also getting. Okay? All right, now, total distance, part F. Total distance is the amount you're traveling, whether you're going forward or backwards. Okay? Think about it. You drive a mile to school, but you forgot something. You drive a mile home, and then you got to go back. So that mile that you went back home is still something you traveled. So when we're doing total distance, we're talking about absolute value or the positive values, right? Whether I was going home or back to school, I'm still driving or moving. So that's the key with total distance. So basically during the first 8 seconds, I need to figure out when I was going in what direction. So that goes back to part D. Okay? I know that I was going in a positive direction from 0 to 1 seconds and then 5 and on. And we're going to go to 8 seconds. So I have to figure out the distance I traveled between 0 and 1 because that was moving in a positive direction. I also need to figure out how far I went between 1 and 5 seconds. That was a negative direction, but I was still moving. And then 5 to 8 seconds because this problem tells me to stop after 8 seconds. Okay, so I need the position. Total distance is a position. So we're using S of t. Okay, position. So I'm going to go from 0 to 1 second. Get that distance. I'm going to go from 1 to 5 seconds. Get that distance. And then I'm going to go from 5 to 8 seconds. So again, why am I using, how do I know that? Okay, so go back to your velocity because I need to know, well, let's look at the graph. I need to know how far I went here before I turned around. That's 0 to 1 seconds. This is when I turned around. So I was going in a negative direction. Obviously, I went past my house and I went somewhere else, okay? So, but still, I went from 1 second to 5 seconds. This is negative velocity, but I'm still moving. And then 5 seconds to 8 seconds, positive velocity, so that's another distance. So I need to figure out my distance. All right, so if it's position, then I'm just going to quickly find these values. These are the numbers I need. S of 5, S of 8, right? So I'm going to plug this into my position function. Easiest way to do that is put that in your calculator and go to y equals. Okay, so I'm going to take the original function, S of t. S of t was t cubed, so I'm going to use x cubed minus 9x squared plus 15x plus 10. Original function. Okay, this guy up here. And just changing my t's to x's so that I could graph it. Well, I don't need to graph it. I just need to go to the table. Okay, so now I'm going to go to the table. Second graph. Delete those numbers out, and I'm just going to put in 0, 1, 5, and 8. Quickest way to get that done. Okay, so there are my values, 10, 17, negative 15, 66. So I'm going to write those down. Okay. All right. So I need to figure out the distance between 0 to 1 second. So absolute value. Okay, so I'm going to do the y values, 10 minus 17, which gives me negative 7, absolute value 7. So between 0 and 1, so at 0 I was at 10, I already knew that, and at 1 I'm at 17. So that means I traveled 7 feet. Okay, makes sense, right? So this is the ordered pair 117. So that distance, still positive, no matter, you could do 17 minus 10, 10 minus 17. It's still a distance, it's still positive. All right, so now I'm going from 1 second to 5 seconds. So I already know this is 117, so this was 5, negative 15. So if I'm going from 17 to negative 15, I'm going to add those, right? Well, subtract, take the absolute value. So I'm basically taking the 17 plus 15 because I'm still traveling. So that would be 17 minus negative 15. You always subtract to do distance and then take the absolute value. So that's going to be a positive 32. And then lastly, I'm going from 5 to 8 seconds. So I would do negative 15 minus 66. And that gives me an absolute value of negative 81, which is 81. So from here to about here, wherever 8 is, right? So I'm going to, those are those numbers right there. Okay. All right. So what is the total distance? I would add that. So I went 7 feet in a positive direction. I went 32 feet backwards, and I went 81 feet back in a positive direction. So 7 plus 32 plus 81 gives me a total distance 120 feet. Okay. All right, so total, so again, use, all we know about the graphs to help you figure that out. We're going to do some more of these in class, so hopefully, if you're still a little confused, okay, we'll talk about it some more when we get to class. All right, let's move on. The rest of these problems, I believe, are from WebWorks. So keep that in mind as you guys work WebWorks. Use your notes, use the hints, okay? All right, so number 24 says the area of a disk with radius r is a of r equals pi r squared. Find the rate of change of the area of the disk with respect to its radius when r is 5. Okay, so again, rate of change. Important that you know that. That's the slope, which means it is the derivative. And in our case, our function is a of r, so our derivative would be a prime. So let's find a prime of r of this function. So a prime of r, now r is your variable instead of x, so that's your, so think of that as pi x squared if you want to. Pi is a constant, so we're going to bring the 2 out front, multiply it by the constant, so that's 2 pi, and then subtract 1 from your exponent, so r to the first. So here's your rate of change function for this area. All right, so now it just wants us to find the area when the radius is 5. I'm sorry, right? Find the rate of change of the area. So we're going to do a prime of 5. So 2 pi times 5, 10 pi. And listen, you can put pi in WebWorks, do that. Remember, if you change pi to 3.14 and put that decimal in there, you will get it wrong. Now, if you change pi on your calculator, okay, and leave that, then that's fine. So do not use 3.14. You can do second pi, leave that whole thing in there times 10. Okay, that would be the number that you would put in WebWorks. If you just put in 31.4, you will get it wrong. If you put in 31.42, you will get it wrong. So this is better to put in there because you don't have to worry about it. Okay, so I keep telling you, don't use decimals if you don't have to on WebWorks. All right, let's look at 25. If f of x equals 3/4 x to the 9th power, then find f prime of x. Okay, this is just kind of a little, not that we're trying to trick you, but this is about the fact that you know how to raise numbers to a power. Okay, so let me move over here, because if you had ab to the 9th, that means a to the 9th, b to the 9th, correct? So we're not trying to trick you here, but this is totally different than if I gave you this. If this was the problem, then the only thing being raised to the 9th power is x, and you would do our rule that we have. That's not what this says, okay? This says this. So that means f of x is really 3/4 to the 9th power times x to the 9th power, okay? So you would have to figure this out, or you could leave it as an exponent, but you would have to raise 3 to the 9th power and 4 to the 9th power. So if I did that, 3 to the 9th power is 19,683. 4 to the 9th power is 262,144, x to the 9th. Now you can take the derivative of f of x. Now, I'm fine with you leaving it like this. WebWorks could leave it like that, so that's okay as well. I just want you to see that is totally different than this. Okay, when you have parentheses around numbers, everything in the parentheses get raised to that power. Okay, so now if I take the derivative, I'm going to do 9 times this. Right, so 9 times this means you're just multiplying 9 times the numerator. So 9 times 19,683 would be 177,147 over 262,144. And then we just subtract 1 from the exponent. Okay, so WebWorks likes problems like these. They just want to make you think a little bit. So again, you could have left this just like that, and then wrote this as 9x to the 8th and just wrote it into WebWorks like that. Okay, I'm just giving you the steps so you can kind of see what we did. All right, look at number 26. It's a product, so we're going to have to distribute. Okay, right now we don't know the product, how to do that. So we're going to have to multiply the square root of x times 3x and then the square root of x times 2. Well, I don't like the square root of x. I need a rational exponent. So we got to do a little work before we find the derivative. So we're going to write square root of x as x to the 1/2. Okay, now we can go ahead and multiply. And remember, when you multiply, you add exponents. Okay, so if we do x to the 1/2 times 3x, that's 3x to the what? 1/2 plus 1 is 3/2. And then x to the 1/2 times 2 is just 2x to the 1/2. All right, so now we have it ready to find a derivative. So now we can find f prime of x. Okay, so we're going to take the exponent, multiply it. So 3/2 times 3 is 9/2. Subtract 1 from 3/2, that gives you 1/2. Plus, multiply 1/2 times 2, that's 1. Subtract 1 from the exponent, negative 1/2. You could put a 1 there, that's fine. So there's your derivative. Okay? Now, how would you write that if you wanted to work with it? Like, let's say I asked you to put in some numbers. So just so you know, you don't have to fix it, but how would you write that? That would be 9 square root of x over 2, because x to the 1/2 is the square root. And then this square root is in the bottom. Okay, that's fine in WebWorks. But if you guys are using this in a problem, a lot of you would get confused about that. So now it would be easier, you know, if I asked you to plug in 9 or something, this would make more sense. Okay, so you just need to be able to move between one form and the other. All right, let's look at 27. I think there's a part B, C on the next page, but let's do 27a. If f of x equals 12 pi squared, then what is f prime of x? This is just so you can kind of see the difference. So let me stick the rest of these up here. Okay, so this is the next page. So look at the difference. They're giving you 12 pi squared, and then for part B and C, they're giving you 12x squared and then 12 pi x squared. These are very commonly missed problems by students because you're going fast and you think, oh, it's easy and I'm just going to do it. 3 different problems, 3 different answers, okay? So in part A, 12 pi squared, those are all constants. This is 3.14. So any derivative of any constant is 0, okay? There is no variable in this problem. Pi is not a variable. Okay, here, 12x squared, that's what we've been working on in this section. We're going to take the power rule, take the exponent, multiply it by the coefficient out front, and then subtract 1 from the exponent. Okay? Now the last one, we have 12 pi is the constant, x is still the variable. So now we're going to take 2 and multiply it by 12 pi. So that would be 24 pi. Subtract 1 from the exponent, so x. Okay, so make sure you pay attention what's a variable, what's a constant, and how those work. Okay. All right, so again, that's a web work problem, so you will see that. All right, last problem, 28, another velocity problem. So it's a good one to end on. So let's look at this. If the ball is thrown, should be if a ball is thrown vertically upward from the roof of a 64-foot building with a velocity of 32 feet per second, its height after t seconds is given by this position function. What is the maximum height the ball reaches? Okay. And then B, what is the velocity of the ball when it hits the ground? Okay, so let's look at part A. What is the maximum height? Well, maximum height would be what? Where V of t equals 0. Think about that. Max height, that would be a maximum. That's where you have a derivative of 0, horizontal tangent line. So that means you're looking for when the velocity equals 0. So we're going to find the velocity function. Okay, so that would be constant, so derivative of that is 0. Derivative of 32t is 32, and the derivative of negative 16t squared, multiply, negative 32t. Set that equal to 0 and solve. So I'm going to move the 32t over to the other side to make it positive. Divide by 32, I get t is 1. Okay? Now, that's not my answer because it says what is the maximum height? This is the time. Okay? So after I find when the velocity is 0, then find the position at that time. Okay, so now that I know 1 second is where I'm going to have my max, now I can find S of 1. Okay, so now I'm going to put 1 into here. 64 plus 32 times 1 minus 16 times 1 squared. Okay, so I got 64 plus 32 minus 16, that gives me 80 feet. All right, so you know me, I'm going to look at this graph and see if that's right. So this is a parabola. I know the y-intercept is 64. Okay, and I know the max is at 1, so that means this graph do something like that. Okay, so right here t is 1, and then I just found the y value up here to be 80. So that looks about right. I knew this parabola opened down because of the negative t squared, right? I know that's the y-intercept, always the constant term. Okay, so I think I'm on the right path. That seems logical as far as that graph looks. Did you need calculus to find the y value of the maximum? No, you can do that right from your calculator, right? But again, we're trying to learn this stuff. So don't cheat and take the, I'm fine with you using your calculator to check it, but you have to be able to do these in this kind of a fashion. Okay, so let's move on to part B. What is the velocity of the ball when it hits the ground? Okay, it says height is 0. Now, a lot of you would say, here's where it hits the ground. This is the position, right? This is the position where S of t equals 0. When the position is 0, the velocity is not 0. Okay? Think about velocity. Velocity anywhere over here is going to be a negative number. Obviously, when it hits the ground, it's going to stop. But when it's falling, it is moving. So when it hits the ground, it is moving at some kind of negative number, right? Negative velocity. That's the slope of the tangent line right here. Okay, if you look at the tangent line right there, it's not zero. Okay, it's a negative slope. So this is another common problem. You guys tend to think when it hits the ground, it has stopped, but when it hits the ground, it was moving. That's the velocity. That's what we need. So what are we going to have to do this? Well, first we need to find the time when this happens, right? We need to find t. And then once we have t, we can put it in here to find the velocity. Okay, does that make sense? So we need t, so we're going to set the position equal to 0, and then we can find the velocity. Okay, so we need to find when does s of t equal 0, then find the velocity at that time. Okay, makes sense? I hope. All right, so we're going to take the position function, set this one equal to 0. Okay, that's what we're looking for, the roots of the original function. And by the way, I'm going to get 2 roots. I don't care about this root because it's a negative time, doesn't exist in the real world, so we want the positive root. Okay, so we're going to take negative, and I'm going to write this putting the squared term first, just so that it's in the right order. So s of t is negative 16t squared plus 32t plus 64. Okay. That's what I want to work on. All right. Now I'm going to set that equal to 0. And you can put equal 0 right over there. That's fine. Now, because I don't like working with negative numbers, I'm going to divide everything by negative 16, even this. So if you divide everything by negative 16, we're not going to change the problem any. That's going to give me a positive t squared number, which is much easier to work with to me. You don't have to do that. And 0 divided by anything is still 0. So now I can work with this much easier. Okay? Because all I'm doing is finding the roots. Can't factor that. So you either can graph it or use the quadratic formula. I'm going to do the quadratic formula just because we may need some practice with that. So t equals negative b. Okay, so negative b would be positive 2 plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is negative 4, all over 2a. So 2 times 1. All right, so that gives me 2 plus or minus square root. Negative 2 squared is 4. And then negative 4 times 1 times negative 4 is plus 16 over 2 times 1 is 2. Let's simplify that a little bit. T equals 2 plus or minus square root of 20 over 2. Just doing this for practice. So 20 I can reduce to square root of 4 times square root of 5. So that's 2 square root of 5 over 2. I can divide 2 into both numerators. So 1 plus or minus square root of 5. Okay? So again, 1 minus the square root of 5 is a negative number. So all I want to do is take 1 plus the square root of 5, which is, again, don't round it so much. Okay. So if I do 1 plus the square root of 5, 1 plus the square root of 5 on my calculator, I get 3.2360679. 8. I'll round it there. I would just leave it like this until you're finished with the problem. So now we're going to find the velocity of this. So we're going to do v of this number, 3.2360679. Okay, so we're going to plug that into here. So 32 minus 32 times that number. Okay, so 32 minus 32 times that. And I'm telling you, WebWorks won't like it if you just put in like 3.23 or 3.24. Okay? So we're going to multiply that out. Now, what I was saying to you earlier is when you do this in your calculator, don't round that. Okay? So I would do 32 times that right now. I would do 32 times and then go get that number, the whole thing. Okay? And then do 32 minus that number. So 32 minus that number. Okay. That's what I would put into WebWorks. So I would get negative 71.554. 1753. That is not rounding, and WebWorks will be happy with you. Okay? And that's feet per second. So like I said, if you round it, you're going to email me and say, I know I'm right, but WebWorks says it's wrong because you're rounding too much. You can only round at the very last step where you're putting in your answer. But you guys see, if you change this to 3.24 and you put 3.24 in here, you won't even get close to that. Okay? So WebWorks is very picky on that. You can put this in WebWorks. Okay? You could, in WebWorks, put 32 minus 32, parentheses, 1 plus square root of 5. Let it compute it for you. That would be better than you trying to round. So just watch yourself on those. Okay? All right. So I know it took a little longer probably than you'd want, but I just wanted, these are kind of important. So I just want to make sure you're understanding how to do these kinds of problems. So let me know if you have any questions. Work on WebWorks. Start now so that it's fresh in your mind. And I'll see you back here next time.